Hi, everyone. Thanks for coming to the Pore Lab seminar. Today we have Mathieu Souzy, and he studies a variety of phenomena kind of in porous media flow, including clogging in suspensions and mixing in porous media. In particular, he's done a lot of three-dimensional imaging of the velocity distributions of flow in porous media and also of the spreading of solutes in porous media. And many of us here are engaged in research similar to this, so we're very happy to have him. So please, Mathieu, start whenever you're ready.
Thank you, and thanks for this very nice invitation and opportunity for me. So as mentioned, today I'm gonna discuss about dispersion, stretching, and more globally, mixing in porous media and transport processes. So which is something I mainly did was working in cooperation with Tanguy Deborn, Yves Meheux, Henri L'Huissier, and Ben Metzger, both in Rennes and in Marseille. So prior to jump into the core of the topic, I would like to discuss a bit more about what we will call in this talk about mixing. So mixing is a process that we all face in our daily based life. Typically in the morning when you take a coffee, you either add some sugar or milk to it, depending on your affinities. And what you want to do is to get your milk being mixed with the coffee. And typically what you will do is take your little spoon and start to stir it within the cup. Because in the end, what you would like to get is the fact to have the milk being homogeneously distributed within your food, so within your coffee. So mixing is this process of getting the concentration distribution being homogenized. And it actually results from two distinct effects which couple to lead to mixing. So the first effect is what you're doing when you're taking your spoon and you're stirring your medium. Basically, what you do is that you generate some advection within the media. So you generate a flow field, and this advection will set two distinct processes which are solely fixed by the kinematic of the flow. And these processes are dispersion, which basically tells you the size of the envelope that will be explored by the milk when you stir it. And the second process, which is fixed by the advection, is stretching. So within this dispersion envelope in which the milk is contained, how does the material line, so the milk you will see, as you see on the picture, start to form some lamellae in 3D? And how does these lamella get elongated within the flow? This is what we call stretching, or also known as elongation. So the advection is going to set these two things: dispersion, how the fluid that you inject is exploring the media around it, and stretching, how within this envelope the material line are getting elongated. But if you're interested in mixing, you need to turn on an extra ingredient, a very key ingredient, which is molecular diffusion. And as you can see on these two images, on the left one, when it's only about advection, so you're stretching your material line, your lamellae, but there is no modification of the concentration distribution. And it's only when you turn on the effect of molecular diffusion that these stretched lamellae will promote the effect of molecular diffusion and the decay of the concentration level, which eventually will lead to the mixing process. So the mixing results from this coupling between these two distinct effects, advection and molecular diffusion. And the first thing that we can very naively predict is that if you have a strong dispersion process, so an advection flow field which is promoting a strong dispersion, it will promote a fast homogenization of your concentration levels. So having this in mind, now we can jump on the question of how does a blob of dye that we would inject in the bulk of a 3D porous medium would mix. So this is typically the kind of experiment that we perform. So here you have a blob of dye, which appear on the image in black, orange. which is pushed within the bulk of a 3D porous medium. And this, what you see is within a slice in the core, in the bulk of the media. And if I make the movie running again, you see that there is a lot of things happening here. And mainly what we see is that the blob of dye is exploring the surrounding media, so forming this envelope of dispersion within which it is contained. And in this envelope, the blob of dye is forming these elongated lamellae. And you see that some lamellae are very strongly elongated, like here. I don't know if you see my mouse, my cursor. Well, anyway, some area are very strongly elongated, and then you see that the concentration level locally decayed, and some are less elongated, and you see that you still have a high level of concentration. So locally, mixing has not occurred yet. So as I mentioned previously, what will be interesting here is that we could quantify what is set and fixed by the advection. So there is the lamellae stretching. So we will, to investigate this, focus on ρ, which is the ratio of the total unrolled length of a lamellae over its initial length L0. And this will provide us what we'll call the stretching law. So how does ρ evolve on average in time? And most importantly, what is the distribution of elongation? So this is set by the advection. And the second thing which is set by advection is the dispersion. So how does the envelope, so which will be defined through sigma x and sigma y on the schematic, how do these quantity evolve in this particular flow field? And these both are important because if you want to predict overall eventually the mixing process, you need to know not only how the lamellae are stretched, but also if they do overlap or not. Because if you have two lamellae which get extremely close one from another, they may merge, and you have to take this into account if you want to fully characterize the mixing process. So stretching by itself is not enough to characterize mixing, dispersion neither, and you really need to consider both and to turn on the effect of molecular diffusion to get a prediction of mixing. So experimentally, to address these questions, this is the experimental setup that we're using. So it's a 3D porous media, which is made of a random bead pack of monodisperse 2 mm diameter spheres of PMMA. So the beads are packed and compressed between two grids to avoid them from moving while we're injecting the flow, the interstitial fluid. So there is no rattlers, no moving beads. The solid phase is steady and not moving. And then with a syringe, we're gonna inject here at the top an interstitial fluid, which will flow within the pores and in between the grains. And this interstitial fluid, so we use Triton X100 as its optical refractive index is very close from those of from the optical refractive index of PMMA at room temperature, such that we can perform direct visualization technique by index matching the whole system. And to finely tune the index matching, the whole thing is surrounded by a water jacket, by a water bath, and by controlling the temperature of the water bath, we're able to adjust the optical refractive index down to the 4th digit to get images with the best contrast and sharp edges of the particles. So the interstitial fluid, as you can see here on the right, is seeded with tiny fluorescent tracers. So it's these white dots on the images. And these are passive tracers, so they are not subject to Brownian agitation. And they are fluorescent, so illuminating them with an horizontal laser sheet, which is made using a laser which impacts a rotating mirror, we can visualize the flow within slices, which are in the bulk of the 3D porous medium. So the idea is to perform a slice like you see on the right. This is typically an example of how the flow look within a slice in the bulk of the media. So when I say in the bulk of the media, I mean that the volume that we're scanning, we're always far from the boundary, from the edge. So we're always 2.5 diameter away from each edge of the system to avoid boundaries effects. And so we get typically these kind of movie within a slice, and we repeat these experiments by scanning the whole bulk of the media. So we do 50 slices in one direction, and then we rotate the whole cell by 90 degrees, and we do again 50 slices in the perpendicular direction of the same volume. So in the end, we have two sets of data, which are both perpendicular one to another. And in each of these images, the idea is to get back using a PIV PTV technique to the velocity component of the flow. So it does involve quite a lot of careful post-processing of the data to make sure that we're not adding any bias by post-processing our data. So typically what we do is that we mask the regions inside the grains where we know that there is no velocity because it's within the grains, within the solid phase of the media. Then, as I mentioned, we have two sets of data which scan the same volume. So we merge them. And once they are merged over the same volume, we can interpolate to get the 3 velocity component over the whole volume. Once this is done, we apply a weighted divergence correction scheme to make sure that the flow that we're measuring is divergence free. And we also apply an extra condition, which is that we know, which is the fact that there is no normal velocity at grains boundaries. So overall, in the end, we end with this 3D velocity field experimentally measure of the porous media, which is divergence free and which is over a total volume of 9D, with D being the diameter of the beads composing the media in the longitudinal direction, and 5D in both transverse directions. So if you want, this velocity field is made available on Digital Rocks portal. It has already been used for benchmark and validation of CFD and the code to compute the flow within porous media. So that could be, for instance, an example of usage that can be do of these data sets. And the spatial resolution that we get doing so is such that we have typically 228 pixels within one diameter of a grain. And on the right, as you can see, we get access to the whole velocity distribution, with U being the longitudinal component of the velocity, and in both the transverse direction, you see that we have a symmetrically distributed exponential distribution of velocities. So now that we have access, that we have measured, quantified experimentally the 3D velocity field of our media, if we get back to our question, initially I told you that if we're able to characterize the kinematic, then we can infer from this the stretching laws and the dispersion, as they are all set by the advection. So the idea here is to get access to the stretching laws, so to the elongation rho and the distribution of elongation. And to do so, we perform material line stretching historial reconstruction, following a method which is called DSM, for diffusive strip method, developed by Meunier and Villermo in 2010. The idea is that within the experimentally measured velocity field, numerically, we're going to inject a small segment, a small line here, which is composed of initially of three tracers, which compose the line, the segment. And we're going to advect these tracers forming this segment inside the flow that we have experimentally measured, to see how the segment is getting elongated within the flow. So typically it goes like this. So you see that it requires to refine the number of tracers which compose the segment, because there's some area which are much more strongly stretched than some other. And so if we do this procedure over a longer time, typically this is the kind of behavior that we observe. So here you have a material line which is stretched on the left in 3D, and on the right you see a projection of the same line segment in the transverse direction. And very interestingly, what we can infer by eyes is that this line is growing with a very fast rate. And if we repeat this process, it's very interesting because it gives a direct access to the distribution of elongation rho. The only thing that we need to do is to compute the total unrolled length at the time t divided by the initial length of the corresponding segment. And so by repeating this procedure, by initially putting the segments randomly within the media and changing its orientation randomly, in the end, we get access to the stretching law, so the evolution of the distribution of rho and the evolution of the corresponding moment in time. So very interestingly here, what I plot is the distribution of logarithm of rho, so the logarithm of the elongation. And if you look on the right, you see that the logarithm of rho is normally distributed, and that as time goes by, the mean value of this normal distribution is increasing, which is what you see on the left plot in red. And the normal distribution is also spreading, so getting wider. And the rate at which the average logarithm of rho is increasing is surprisingly very similar to the rate of increase of the variance of logarithm of rho. And most interestingly, if the logarithm of the elongation is normally distributed, it means that the distribution of rho, of the elongation itself, is log normally distributed. And from the mean value of logarithm of rho and of the variance of logarithm of rho, we can get back to the corresponding moment of the associated log normal distribution of rho, which is given here. And so what we see here is that on average, the evolution of the average rho is exponentially increasing in time in 3D porous media. And this is actually a quite important and striking result. If you would, for instance, do the same process, but you forget about the porous media, you just put a blob of ink in a shear cell and you just move the wall both in one direction and the other. So in this situation, you would have a linear increase of rho in time. And here, by investigating the flow within a 3D porous media, what you see is that the nature of the stretching law is not linear, it's not a power law, it's exponential, which means that the elongation is extremely strong within 3D porous media. Interestingly, some people have investigated this, so Tanguy de Born, in 2D porous media. And in 2D porous media, what they found is that it's not an exponential stretching, but a power law. So the elongation is not going like an exponential, but like t to the power beta, with beta being larger than 1. And so what explained the difference between the fact that in 2D porous media you have a power law stretching, while in 3D porous media you have exponential stretching. The way we understand it is that in 2D porous media, when you're a fluid element and you get in front of an obstacle, in 2D you only have the choice to go left or right to avoid the obstacle. While in 3D you have an extra degree of freedom, which is that you can go up and down, up and below the obstacle. And this extra degree of freedom is what's make it such that in 3D porous media, the stretching laws are quantitatively very different and in nature from those in 2D porous media. So what we have seen is that from the experimental measurement of the flow within a porous media, we can infer and get access to the stretching laws. But there is also another thing that we discussed, which is the dispersion process. So to investigate dispersion, the first thing that we can do is getting back to the lab, and instead of injecting a blob of dye within the porous media, we can inject a cloud of a suspension of non-diffusive tracers. So this is what happened if you do such experiments. So here, if you look carefully, you see that it's basically a cloud of very tiny black dots on the image. And all these tracers, so they are non-diffusive, they are large enough such that they are not subject to thermal agitation. And here, the question that we're interested in is to quantify the evolution of sigma x and sigma y, which will characterize typically the size of the envelope of dispersion, while the blob, well, the cloud is pushed within the porous media. So if we do experimentally such characterization, this is what we get. So here it's the variance, the non-dimensionalized variance, which is plot sigma square and in x, so in the longitudinal direction, and sigma square in y, so in the transverse direction. And we get these kind of results. So they are not extremely surprising. What we see is that initially we get back to the ballistic regime, which is expected. So dispersion process at the short time, you're expecting a ballistic trend, so with a power law of 2. And then it moves from the ballistic regime to an anomalous regime. Anomalous meaning that both in the longitudinal direction and the transverse direction, you don't have a normal dispersion process with a power law which would be 1. So in the longitudinal direction, it's actually super diffusive with an exponent of 1.4. And in the transverse direction, you have a subdiffusive anomalous dispersion process with an exponent which is below 1, so 0.7. So that's the first way you can decide to investigate dispersion in such system. But it happened that as we have access to the 3D velocity field, we can also do the exact same procedure, but numerically. So this time, instead of experimentally putting a cloud of non-diffusive tracer and seeing how they explore, we're going to do the same thing, but numerically. So initially, you put a cloud of points, and you just let them getting advected individually within the flow. And you see that some explore some streamlines and some get on some other path, and that although initially they all look like close by, at the end they explore very different paths, which is a signature of how tortuous the flow is within porous media. And if you repeat this over a large number of points which are randomly initially placed in the media, this is typically the kind of results that we get. So again, we get back to what we experimentally measure, so a ballistic trend at the short time, and then we get the anomalous regime that we observe experimentally. But most interestingly, with these numerical advection, we can go to time, we can explore times which are higher than what we can experimentally access. And when you do so, very interestingly, what we see is that both in the longitudinal direction and in the transverse direction, we eventually tend to a Fickian dispersion, so a normal dispersion process where the power law is going back to a value of 1. And this is actually quite surprising. So now if we want to get back to understand the origin of these dispersion laws, we will have to make one step back and to focus a bit on the velocity distribution measurements. So typically when you're measuring a velocity using PIV or PTV technique, there is always a range of accuracy within which your procedure is able to accurately measure or quantify the velocity that you're measuring. And in these porous media, it happened that the range of velocity distribution is so wide that it's very difficult for a PIV or PTV measurement procedure to be able to be accurate within the whole range of explored velocities. So what we had to do is to make dynamic range velocity distribution. Basically, the idea is that with the images that we got from the slice that I showed you initially, a slice of PIV, we can perform a first run of PIV, which will PTV actually, which will focus only on characterizing and quantifying the high velocity within the slice. So typically all the yellow area here, it's area where the velocity are large enough and are characterized here. And then instead of doing the PIV, PTV measurement over one frame and the next frame, we can do it over one frame and then skip 10 frames. And therefore you have access to a velocity range which is lower, which is the light blue that you see here. And these light blue area are represented here in light blue too. So this allows you to get access to the velocity in a different range, which is lower than the previous one that you did. And if you do the same thing again, so PIV, PTV, but not between frame n and frame n plus 1, but frame n plus 100, then you're able to quantify the very, very low velocity within your system, which is in dark blue here. So only these very tiny dark blue area on the slice here. And when we do this, what we see is that actually we have a distribution of velocity which is flat at low velocities. And this is actually a very important result, because since the work of Berkowitz in 2006, where he investigated the kind of dispersion process that one should get theoretically from a flat distribution, he predicted that if you have a flat distribution of velocity at low velocity, the dispersion process should be anomalous at long time, going like t log t. So how does it happen that in the experiment, at long time, we have a Fickian dispersion? We experimentally measure a flat velocity distribution. So how do we solve this apparent paradox? To solve it, we have to invoke the fact that in our experiment, there is always a minimum cutoff velocity, which is either fixed by the size of the tracer that are exploring your media. So typically in our experiment, the tiny tracers that we were using, they are very tiny, but still not tiny enough to explore the extremely close from the solid phase boundaries, where you have these extremely tiny velocities of the flow. So this means that they cannot explore the whole range of the velocity distribution. And it's either fixed by the tracer finite size, either if your tracers are even smaller, so you feel like, okay, they're very small, so they can explore this area, then they get they get so small that they are themselves subject to thermal agitation. And therefore, it also sets a minimum cutoff velocity, which will not allow you from ever exploring these very low velocity of the fluid. So in the end, the important thing to remember here is that you always have in your experiment a minimum cutoff velocity, U min, which will set the range of velocity which will be prohibited from being explored in your system. And this minimum cutoff velocity sets the fact that their dispersion process will become Fickian beyond a time which is itself fixed by the value of this minimum cutoff velocity. So to test these hypotheses, these IDs, what we can do is a continuous time random walk, which is very often used. So it's basically you provide to the continuous time random walk a given velocity distribution, and it will predict the dispersion process that you will get out of it. So if we do a continuous time random walk using a flat velocity distribution, so being flat at low velocity, we see that we get the green line here, so which goes like t log t for a large time, as predicted by Berkowitz. Now, if we do the same thing, but we use a minimum cutoff velocity such that all this area of the velocity distribution is prohibited, then we see that eventually the regime tends to a Fickian dispersion process, and the higher the minimum cutoff velocity, the faster we tend to this Fickian regime. And eventually we get back to the result that we measure experimentally with so moving to a Fickian regime for these value of the minimum cutoff velocity. And this we can do it both in the longitudinal direction, but also in the transverse direction using some anti-correlation in the continuous time random walk. And here again, we get back to something which is very similar from what we measure experimentally. So as a summary, by experimentally characterizing the flow kinematic within the bulk of a 3D porous media, first we get access to the 3D velocity field. And from these, we can infer and get a lot of information about the advection process and how it's set the stretching and dispersion processes. So on the stretching laws perspective, we see that there is a log normal distribution of stretching with average elongation, which are exponentially growing in time. And on the dispersion process, we see that there is an anomalous transient behavior, but which will eventually tend to a Fickian dispersion regime after a time TF, which is in turn set by the minimum cutoff velocity that you always have in your system. So now, as I still have a little bit of time, I'm going to show you something, also some project that we had. So in addition from using the velocity field for doing these quantification of stretching and dispersion, we also used it to develop, so it's a 3D velocity field explorer called Pore Aventura. So it's an open source software that is available on GitHub, which aim to allow the user from, I don't know if you have the sound, which allow the user from exploring the bulk of porous media. So you can travel within the microstructure, you can inject some tracers to see how they flow on their own streamlines. You see that there are a lot of feature available. So here you can see the streamlines, where they start and where they end. And it allows to basically visualize and see how complex and tortuous the flow can be within the bulk of a porous media. So it's still an ongoing project where we're still adding some feature, but that's also to show you the kind of thing that could be done with these kind of data sets. And for the future and the ongoing work, so as we're all aware of, porous media is a very rich system where the flow within such media can lead to a very rich phenomenology. And the idea for the ongoing work that we're starting now in X is to focus on moving toward more complex microstructures. So everything I showed you so far is in the model porous media, which is made of a random bead pack of monodisperse beads. So now we're going to investigate the effects of adding step by step some more complexity to the microstructure to decipher what are their effects over the transport processes. So it starts with investigating the effect of polydispersity. So this will tend to widen the distribution of pore size, and so how does this affect the dispersion and stretching processes? You can also think about the effect of a crack. So when you have in soil samples, so some channel of erosion, how do they affect the dispersion process? So experimentally, by putting a tube which mimic a crack within the bulk of a porous media, how will this affect these processes? So typically you can think that if you have such tube, so channel within the bulk of the media, will it promote the fact that some of the injected dye would travel through these kind of highways in the bulk of the media and therefore alter dramatically the dispersion process? But you can think of other tiny local heterogeneities. So overall, the idea is to investigate the effect of all these local heterogeneities to see how the mechanism going at the pore scale affects overall the velocity distribution and transport processes of the soil and of the porous material. And on a future perspective also, on the same following idea of going toward more complex microstructure, we have the idea of investigating and elaborating 3D printing technique of transparent porous media. So here the idea is that you would take a soil sample, you scan it by X-ray tomography. And from the knowledge of its microstructure, you would 3D print it in a transparent media. And therefore, once you manage to have such 3D prints, you could use it to perform all these kind of direct visualization technique approach to characterize the flow kinematic in such system. And also one of the strong assets of such technique is that if you're able to print such sample, you could also decide to locally alter, to locally put a small heterogeneity, like locally you increase a pore or you close it completely, and what will be the effect of such modification over the flow within the media. And we're in this, there is also some other effect that we're willing to jump onto to address, notably the effect of clogging. So as you can see here, even if you consider only a single pore with a suspension going through the single pore, you see that depending on the ratio of the size of the fine particle and the size of the constriction, you can have some very interesting behavior like intermittent regime clogging like you see here. And these will bring some dynamic modification and to the flow field. So how would these affect the overall transport processes? And this is particularly relevant considering that during erosion or suffusion process, you can have such mechanism at play. And so we're actually, especially on these questions, we're right now looking to hire a PhD to start on working on these questions starting in fall. So if you know anyone who would be interested in investigating such question back here in France, in Aix-en-Provence, it's very sunny and a nice place. So please feel free to let us know. And with this, I thank you for your attention and I'm available if you have any more questions.